Bismillahirrahmanirrahim. The ability of hemoglobin to reversibly bind oxygen is affected by the partial pressure of oxygen or PO2, the pH of the environment, the partial pressure of carbon dioxide, and the availability of 2,3-BPG. These are collectively called allosteric effectors because their interaction at one site on the tetrameric hemoglobin molecule causes structural changes that affect the binding of oxygen to heme iron at other sites on the molecule. The tertiary structure of hemoglobin consists of 8 alpha helices connected by short coils. This structure is known as globin fold and it is unusual for a globular protein because it has no beta sheets. These helices form a hydrophobic oxygen binding pocket containing a tightly bound heme with an iron atom in its center. Heme consists of a planar porphyrin ring composed of 4 pyrrole rings linked by methynyl bridges that lie with their nitrogen atoms in middle, binding with an iron atom in the ferrous form in its center. Negatively charged propionate groups on the porphyrin ring interact with positively charged arginine and histidine side chains on the hemoglobin. The hydrophobic methyl and vinyl groups that extend out from the porphyrin ring interact with hydrophobic amino acid side chains from hemoglobin, positioning the heme group within the protein. Altogether, there are 16 different interactions between hemoglobin subunit and different groups in porphyrin ring. Organic ligands like heme that are tightly bound are called prosthetic groups. Within the binding pocket of the hemoglobin and myoglobin, oxygen binds directly to ferrous atom. The ferrous atom is able to chelate or bind 6 different ligands. 4 of the ligand positions are in a plane and belong to the nitrogens of the planar porphyrin ring. There are 2 ligand positions perpendicular to this plane. One belongs to nitrogen atom on histidine called the proximal histidine, which extends down from a myoglobin or hemoglobin alpha helix. The other position is taken up by oxygen, carbon monoxide, or it may be empty. The proximal histidine of hemoglobin and myoglobin is sterically repelled by the heme porphyrin ring. As in the absence of oxygen, the ferrous is not in the plane of the porphyrin because the iron is too large and heme is puckered. However, upon oxygen binding, the shared electrons result in slightly smaller atomic radius for ferrous, allowing it to move into the plane of the porphyrin ring. So when oxygen binds on the other side of the ring, it pulls the ferrous back into the plane of the ring. The pull of the oxygen binding moves the proximal histidine towards the porphyrin ring, which moves the helix containing the proximal histidine. This conformational change has no effect on the function of myoglobin. However, in the hemoglobin, the movement of one helix leads to the movement of other helixes in that subunit, including one in a corner of the subunit that is in contact with a different subunit through ionic interactions or salt bridges. The cooperativity in oxygen binding in hemoglobin comes from conformational changes in tertiary structure that take place when oxygen binds. The conformational change of hemoglobin is usually described as changing from a T or taut state with a low affinity for oxygen to an R or relaxed state with high affinity for oxygen, breaking the salt bridges in the contacts between the subunits, and this is an energy requiring process, and consequently the binding rate for the first oxygen is very low. When the next oxygen binds, many of the hemoglobin molecules containing one oxygen will already have all 4 subunits in the R state or relaxed state, and therefore the rate of binding is much higher. With 2 oxygen molecules bound, an even higher percentage of hemoglobin molecules will have all 4 subunits in the R state. This phenomena is known as positive cooperativity and is responsible for the sigmoidal oxygen saturation curve of hemoglobin. The binding of protons by hemoglobin lowers its affinity for oxygen, contributing to a phenomenon known as Bohr effect. The pH of the blood decreases as it enters the tissues and the proton concentration rises. Because carbon dioxide produced by the metabolism is converted to carbonic acid by a reaction catalyzed by carbonic anhydrase in red blood cells, dissociation of carbonic acid produces protons that react with several amino acid residues in hemoglobin, causing conformational changes that promote release of oxygen. In the lungs, this process is reversed. Oxygen binds to hemoglobin because of high oxygen concentration in lungs, causing release of protons which combine with bicarbonate to form carbonic acid. This decrease of protons causes the pH of the blood to rise. Carbonic anhydrase cleaves the carbonic acid to water and carbon dioxide, and the carbon dioxide is exhaled. Thus, in tissues in which the pH of the blood is low, because of the carbon dioxide produced by the metabolism, oxygen is released from hemoglobin. In the lungs, where the pH of the blood is higher because of carbon dioxide being exhaled, oxygen binds to hemoglobin. Although most of the carbon dioxide produced by metabolism in the tissues is carried to the lungs as bicarbonate, some of the carbon dioxide is covalently bound to hemoglobin. In the tissues, carbon dioxide forms carbamate adducts with the N-terminal amino groups of deoxyhemoglobin and stabilizes the deoxy conformation. In the lungs, where the partial pressure of oxygen is high, oxygen binds to hemoglobin and this bound carbon dioxide is released. Now, let's consider one by one the agents that affect the oxygen binding. 2,3-BPG or 2,3-bisphosphoglycerate is formed in red blood cells from the glycolytic intermediate 1,3-bisphosphoglycerate. 2,3-BPG binds to hemoglobin in the central cavity formed by the 4 subunits, increasing the energy required for the conformational changes that facilitate the binding of oxygen. Therefore, oxygen is less readily bound, that is, more readily released in tissues. When hemoglobin has a bound 2,3-BPG, red cells can modulate oxygen affinity for hemoglobin by altering the rate of synthesis or degradation of 2,3-BPG. One molecule of 2,3-BPG binds to a pocket formed by 2 beta globin chains in the center of the deoxyhemoglobin tetramer. A plot of percent saturation with oxygen measured at different partial pressures of oxygen is called the oxygen-dissociation curve. The curves for myoglobin and hemoglobin show important differences. The graph illustrates that myoglobin has a higher oxygen affinity at all PO2 values than does hemoglobin. The partial pressure of oxygen needed to achieve half saturation of the binding sites is 1 mmHg for myoglobin and 26 mmHg for hemoglobin. The higher the oxygen affinity, the more tightly the oxygen binds, the lower the P50. The oxygen dissociation curve for myoglobin has a hyperbolic shape. This reflects the fact that myoglobin reversibly binds a single molecule of oxygen. Thus, oxygenated and deoxygenated myoglobins exist in simple equilibrium. The equilibrium is shifted to the right or left as oxygen is added or removed from the system. The myoglobin is designed to bind oxygen released by hemoglobin at low partial pressures of oxygen found in muscle. Myoglobin in turn releases oxygen in muscle in response to oxygen demand. The oxygen dissociation curve for hemoglobin is sigmoidal, indicating that the subunits cooperate in binding oxygen. Cooperative binding of oxygen by 4 subunits of hemoglobin means that the binding of an oxygen molecule at one subunit increases the oxygen affinity of the remaining subunits in the same hemoglobin tetramer, as shown by the steep upward curve in region near 20 to 30 mm Hg. The steep slope of the oxygen dissociation curve over range of oxygen concentration that occur between lungs and the tissues permits hemoglobin to carry and deliver oxygen efficiently from sites of high to sites of low partial pressure of oxygen. Let's see the effects of allosteric effectors on oxygen hemoglobin dissociation curve. Decrease in pH results in decreased oxygen affinity of hemoglobin and therefore a shift to the right in the oxygen dissociation curve as shown by the red curve. Hemoglobin from which 2,3-BPG has been removed has high oxygen affinity. The presence of 2,3-BPG significantly reduces the oxygen affinity of hemoglobin, shifting the oxygen dissociation curve to the right as shown by the red curve. The reduced affinity enables hemoglobin to release oxygen efficiently at partial pressures found in the tissues. The concentration of 2,3-BPG in RBC increases in response to chronic hypoxia, such as observed in chronic obstructive pulmonary disease like emphysema, or at high altitudes where circulating hemoglobin may have difficulty receiving sufficient oxygen. Or intracellular levels of 2,3-BPG are also elevated in chronic anemia, in which lower than normal RBCs are available to supply the body's oxygen needs. Elevated 2,3-BPG levels lower the oxygen affinity of hemoglobin, permitting greater unloading of oxygen in capillaries of tissues. 2,3-BPG is essential for the normal oxygen transport function of hemoglobin. However, storing blood in currently available media results in gradual depletion of 2,3-BPG. Consequently, the stored blood displays an abnormally high oxygen affinity and fails to unload its bound oxygen properly in tissues. Thus, hemoglobin deficient in 2,3-BPG acts as an oxygen trap rather than as an oxygen delivery system. Transfused RBCs are able to restore their depleted supplies of 2,3-BPG in 6 to 24 hours. Stored blood is therefore treated with a rejuvenation solution that rapidly restores 2,3-BPG. Carbon monoxide binds tightly but reversibly to hemoglobin iron. When carbon monoxide binds to one or more of the four heme sites, hemoglobin shifts to the R conformation, causing the remaining heme sites to bind oxygen with high affinity. This shifts the oxygen hemoglobin curve to the left and changes the normal sigmoidal shape to hyperbola, as shown by the black curve over here. As a result, the affected hemoglobin is unable to release oxygen to tissues. The affinity of hemoglobin for carbon monoxide is 220 times greater than oxygen. Consequently, even minute quantities of carbon monoxide in the environment can produce toxic concentrations of carboxyhemoglobin in